Good afternoon, everybody. Welcome to lecture. It's 11:30, so time to get started. Announcement, big announcement. Exam 2 is coming up. It's going to be Monday. It's going to be here in class. Unless you've got some sort of accommodation, you'll be taking it at a different place or whatever. But everybody else comes here, takes it on the 27th. See Canvas for the full information on that. It follows the syllabus. It's the same sections and the same content that we've been covering since the last exam, and it's described in the syllabus. But Canvas gives you a little information on what kinds of resources you're going to get. So, and practice exams are there too, so it's worth checking out that module. I have one more molecule of the day for you right here. So this is the 5th of 5 molecules of the day that will be on exam 2. This one I selected because it bridges the functional groups that we've been talking about in the last chapter with the functional group we're talking about in the current chapter, and that is this molecule called nicotinic acid. It goes by other names. It's sometimes known as niacin or vitamin B3. The thing is these are terms that can refer to very structurally similar molecules. Like if you put a nitrogen here and make it into an amide, that's also considered niacin and vitamin B3. But nicotinic acid refers to this one specifically. So carboxylic acid, that's where we're going in the next chapter. And then pyridine ring. So remember, this is a aromatic ring. It's got 6 pi electrons. It has a nitrogen, which has a lone pair, and that lone pair is basic. It's not a real strong base, so it's not quite strong enough to really pull the carboxylic acid proton off, but compared to other nitrogens that are in aromatic rings where their pi electrons are counting towards getting 4n plus 2 pi electrons, these are much, much more basic than that kind of a nitrogen, like in the pyrrole ring, for example. So this is an essential nutrient. It is important in a lot of physiological processes. And it's the 3rd vitamin that we've had in molecules of the day, which sounds like it could be confusing, but they have really different structures. So if you can remember, nicotinic acid, the name tells you acid, so that's a pretty big clue that this one has a carboxylic acid in it. That might make it easier to match. Remember, you're going to match names with structures, so you don't have to reproduce these structures. You just have to pattern match between names and functions and then the structure. So that's what's coming up. Okay, let's talk about some survey questions that are related to the content that we finished on last time. So there were 2 survey questions that you were asked about. Here's a molecule right here, and here's a molecule right here. And the questions were the same, just 2 different versions of the question with 2 different molecules. Question wanted to know what was the preferred conformation, flat or puckered, and what is its state when it's in that preferred conformation? Is it going to be aromatic, non-aromatic, anti-aromatic? And there are a bunch of options. So the key to this one is, first of all, establish that the rules that generally apply when we're looking for aromatic or anti-aromatic rings that they hold, like it's got to be a ring, it's got to be fully conjugated with an unbroken ring of overlapping p orbitals, so every atom has to have a p orbital on it. And then if it's flat and it's got 4n plus 2 pi electrons, it'd be aromatic. If it's flat and has 4n pi electrons, it'd be anti-aromatic. But a lot of times these molecules, if they're anti-aromatic when they're flat, they'll pucker to become non-aromatic, which is better than anti-aromatic. Remember, the hierarchy is aromatic is very stable, very low energy. That's the best place a molecule can be. So if it can get flat and become aromatic, it wants to do that. If it were to be non-aromatic, in other words, if it were not flat, it'd be non-aromatic, and that's a little higher in energy. It's not as good as aromatic, but it's certainly not as bad as the other option, which is anti-aromatic, which is way up in the air. High energy because it's got a special instability. So you got to count pi electrons. And with this one, it's pretty straightforward because there's just carbon-carbon double bonds. So just count, start in one spot, and make sure that you don't double count or miss one. But I'm going to go 2, 4, 6, 8, 10, 12. So this molecule has 12 pi electrons. And that is a multiple of 4n. It's an even multiple of 4, which means that this is set up to be anti-aromatic if all the rules hold. If it's flat, then it's going to be anti-aromatic. So that is not a good way to live if you're a molecule. So what this molecule will want to do is pucker out of planarity to become non-aromatic. So the preferred conformation is puckered. And any puckered molecule will always be non-aromatic because puckering breaks conjugation. The p orbitals can't overlap if they're not parallel, and so that makes this non-aromatic, and it basically avoids anti-aromaticity for this molecule. So that's what it likes to do, puckered and non-aromatic. Then we got this molecule over here, which is a bigger ring, and it's got a lone pair of electrons, so we have to figure out how to handle those. First thing to do is like address this charge and figure out what's going on there. And remember, you got to apply that XYZ rule whenever you've got a lone pair on an atom in one of these rings to see for sure that it's sp2 hybridized. So this goes XYZ if you consider it in that direction, or XYZ approach from that direction. So what that means is that atom is sp2 hybridized, and the lone pair is in a p orbital. So they count as pi electrons. And that's what you have to do when you're counting electrons, is include 2 for the lone pair. So let's count around and get all the ones from the double bonds and then add 2 there. So we'll go 2, 4, 6, 8, 10, 12, 14, 16. So this one has 16 pi electrons. And this is another system that's a multiple of 4. This is a 4n system. So in other words, this is another one of those combinations of pi electrons that would lead to an anti-aromatic ring if it were flat. So this molecule is going to want to avoid being flat, because being flat means it's anti-aromatic. It means it's really high in energy. It doesn't want to do that. So it's going to pucker out of planarity. That'll make it more stable. It will make it non-aromatic. So this one has the exact same answer. It's a puckered molecule, and it is non-aromatic. So that's a good little bit of review about how to count pi electrons in aromatic rings. And hopefully that makes sense. Any questions about that? Yeah, question.
Can you just explain again why it would pucker and why it would be flat?
Okay, well, let's consider the 2 scenarios. So the question is why would it pucker, why would it be flat? Let's consider 2 scenarios. So first of all, there are 2 ways this molecule could exist. It could lay itself into a flat conformation, or it could bend itself and be puckered. Okay, both of those are like that. It's the flexibility of the molecule that allows it to do that. So when this molecule is flat, and actually the answer to these is going to be the same because these both have the same characteristics. When these molecules are flat, they are anti-aromatic. So because they follow all the rules, they are a ring, they are flat because we're assuming they're flat, and they're fully conjugated, which means, and they have 4 pi electrons. And so that series of traits means that they're anti-aromatic. They are anti-aromatic, and I'm going to say very unstable. So if this molecule were to select the flat conformation, it'd be very unstable. When these molecules pucker out of planarity, in other words, they bend, they are no longer conjugated and are just non-aromatic. And I'm going to just highlight, the anti-aromatic option is very unstable. Non-aromatic is just normal stability. The molecules adopt the lowest energy conformation. they don't want to be very uncomfortable. Think of conformations as kind of like, how you would adjust your posture. Okay, it's kind of like molecular posture. You could try to touch your toes, for example, but for me, this is very uncomfortable. I don't want to hold this pose very often. So this is a conformation. This is my anti-aromatic conformation. I'm not going to do that anymore. If I were better with my flexibility, it wouldn't be so hard, but that was kind of uncomfortable. So rather than be very unstable, I'm gonna straighten up and be just normal stability. If I sat down, I'd be even more stable, but I can't do that right now. I don't know if that helps or not, but basically, these molecules can adopt different conformations. They can either flatten out or they can be puckered, and they'll do whatever makes them more stable. If the molecule benefits from aromaticity by being flat, then it'll want to do that. And if it is penalized for being flat by being anti-aromatic, it'll avoid being flat. So it's all about what makes the molecule most stable. So that was the point of this. So I'm glad you asked the question, because it's a good discussion of that, and really the driving force behind why they adopt the conformations that they do. All right, let's talk about carboxylic acids. Carboxylic acids are an interesting and very important class of functional group that contain a carbonyl. In the textbook, we don't get to this. If you followed the textbook linearly, this chapter wouldn't come up until a bit later. It's chapter 15 in the 7th edition of the Smith textbook. But we're going to hit it now because it's easy and it's a quick one to slip in. And carboxylic acids are they're interesting. So let's talk about carboxylic acids in chapter 15. Here's the general structure of a carboxylic acid. It's got a C double bond O that's also attached to an O that's attached to an H. The key feature is that this proton is acidic, much more acidic than a typical H, even more acidic than an OH, like an alcohol OH. So this is, if you just look at the right side of it, it kind of looks like an alcohol, but connecting it to a carboxylic acid or a carbonyl makes a carboxylic acid, which is a lot more acidic. The pKa values for these depends a lot on what R is, but I'm going to say they're about 5 for a generic carboxylic acid with an alkyl group here. So that's pretty acidic. Most other OHs and NHs and CHs are a lot less acidic. These things are abbreviated. So if you're looking at condensed structural formulas, you might see the molecule abbreviated like that, RCO2H. So you got to recognize that as being, when you see that, you should think carboxylic acid. You might also see it written as RCOOH, which I don't really like this representation, because it sort of seems to suggest that the two O's are bonded, but they're not. So this is an important thing to keep straight, is both of these representations are talking about this structure. So they should both tell you carboxylic acid. Okay, and in all these cases, it's the H there that gives them their unique chemistry, makes them acidic. So what we're going to do is we're going to look at basic nomenclature for carboxylic acids. Nothing too fancy, nothing real difficult, but just getting you started on naming these things. It's pretty easy. As far as functional groups go, carboxylic acids are one of the easier ones to name. Naming. Carboxylic acids. I had previously made some videos talking about naming of carboxylic acids that I'm going to post in Canvas or link in Canvas so that you can see them for a kind of a more detailed, in-depth discussion of naming carboxylic acids. But here are the basics. Let's put up a carboxylic acid and chat about it. Find the longest carbon chain that contains the COOH. In other words, the longest carbon chain must include the carbon of the carboxylic acid. So find the longest carbon chain that includes the carboxylate carbon, that carbon right there. It's very similar to how we operated when we were naming alcohols. When we were naming alcohols last semester in Organic 1, we had to find the longest carbon chain that had the OH attached. It's a very similar kind of rule here. And if you want to, you can just start at the carboxylic acid carbon and count in all different directions to try to find the longest carbon chain. It's a good strategy. Once you find it, then that forms the parent name or the root name. So this is, let's count it, 1, 2, 3, 4, 5, 6, 7. So it is a 7-carbon chain. And what you do is name as the alkane. We're going to use that as our base naming. So if this were an alkane, it would be heptane. And then change the ending. So what we're going to do here is we're going to get rid of the E and we're going to substitute hept. And instead of the E, we're going to go oic and then space acid. So this is the bit there that's new. So we got rid of the E and we're adding oic acid to it. And the carbonyl defines the number 1 position. And so you don't need to include it in your naming. If we were going to number this thing to locate substituents, we don't have any substituents here, but if we did, we'd want to number the chain starting at the carboxylic acid carbonyl, carboxylate carbon. Go 1, 2, 3, 4, 5, 6, 7. And with this molecule, it's just as simple as calling it heptanoic acid. And there is a space between heptanoic and acid, which electronic homework platforms will ding you on if you don't include that. It won't recognize it as correct. It probably will give you feedback telling you, hey, you need a space. But this is the one rare instance where a space is required in a name. All right, let's look at one that's a little bit more complicated, not a lot, but has at least something else attached to it. All right. Here's an interesting structure. Let's name it. We should find the longest carbon chain. That includes the carbonyl carbon, the carboxylate carbon, the one that's making the carboxylic acid functional group. If you just looked at this molecule and you tried to find the longest carbon chain, any longest carbon chain, you'd go 1, 2, 3, 4, 5, 6, 7. But the problem is that carbon chain doesn't include the carboxylic acid carbon, so it doesn't count. So we have to start here, and we'll go 1, 2, 3, 4, 5. That's better than starting here and going 1, 2, 3, 4. Oh, wait. Oh, they're 5. I want to do this. Sorry. I just want to make them different so that it helps you remember the rule, basically. So this would be the longest carbon chain then that contains the carboxylic acid carbon. And these things will get numbered 1, 2, 3, 4, 5, 6. So it's got a 6 carbon longest chain. So it's going to be a hexane if it were an alkane. Hexanoic acid is going to be the root name for this thing. Hexanoic space acid. And we don't need to say 1 for the hexanoic acid because everybody knows the carboxylic acid carbon is at the number 1 position. But we do have to tell people that there is a propyl group in the 3 position. So there's a 3 propyl group, and that goes out in front. Oh, is there a question?
Would it be at the 2 position?
Oh, you're right. It is a 2 position. Yeah, I don't know how I missed that. Thank you. Yeah, that's definitely true. 3 is over here. Yeah, attached to the 2 position. Nice catch. All right, so we're going to go to propyl with no space, hexanoic space acid. Good. There is a stereogenic center here, but there's no stereochemistry that's indicated. You can use the standard RNS nomenclature to identify stereogenic centers if you have them, but I'm not going to make that a focus of this exam because we just, we talked about stereochemistry before and naming. So anyway, just be aware that there can be R and S stereogenic centers, and then you find the stereogenic center. If it's in the 2 position, you figure out whether it's R or S, and you'd say 2S in front, 2-propyl hexanoic acid. So, all right, there are a couple other scenarios that'll come up, so I want to just prep you for those. Sometimes you have carboxylic acids that are attached to rings. So, for example, this one. So, when attached, when CO2H is attached to an alkane ring like this, name it as a cycloalkane and add carboxylic acid. So this molecule then, the name of this thing would be cyclohexane carboxylic acid. It's just an easy way to name it. And if you had any substituents on it, the carboxylic acid defines the number 1 position. So if there was say a methyl group here, let's just look at an example of this. You start at 1, and you don't have to specify the position of the carboxylic acid because, again, it's assumed it's assigned to the 1 position. But you number around the ring to give low numbers to the groups. And so this would be the 2 position then. So the name of this molecule would be 2-methyl. Cyclohexane carboxylic acid. Okay, pretty easy to apply those rules. One other reminder, It's a bit of a flashback to the last chapter, but when you have a carboxylic acid attached to a benzene ring, those have their own special names. And it is benzoic acid. Yeah, I believe there is. I think so. I think those are considered separate names. Almost positive about that. So when you have carboxylic acid on a benzene ring, remember this has a special parent name. It's called benzoic acid. It was one of those about 6 or so examples of root names for benzene rings that you need to remember for exam 2. Benzoic acid. It just turns up here because we're in carboxylic acid chapter. There are some common names that I want to just list off for you because you're going to see these things over and over again, not just in chemistry, but in biology or any kind of lab if you go into. The systematic name isn't always the one that gets used commonly. So here are some important carboxylic acids that have common names that are more popular. So this one is called formic acid. Its common name is formic acid. You don't need to remember these for the exam. If you were going to name this systematically, you'd call it methanoic acid, but nobody calls it that. It's always formic acid because it's been known for a long, long time. It comes from, historically, formica it's Greek or Latin maybe for ant, and it's in ant venom. So basically there's a historical reason why it's called formic acid. This one is called acetic acid. This is a really important name to know because it's a really common acid, and it's important in lots of different contexts. But acetic acid is what people would call this. It's got a systematic name, ethanoic acid, but nobody calls it that. So that's one to be aware of. And you can get versions of these acids that are bigger, and they start to have names that kind of sound systematic. So sometimes the common name is pretty close to the systematic name. This would be systematically naming it. It's propane, so it would be propanoic acid. The common name for this is propionic acid. So you might see it as propionic acid. It's propanoic acid is the same thing. So I just want to put down here propanoic acid. These are synonyms. It's just aliases for the same molecule. And a lot of times molecules have lots of names. If you look at PubChem and look up a molecule, sometimes you'll see many, many different names for a given molecule. Like, for example, molecule of the day, nicotinic acid, vitamin B3, niacin, lots of different aliases. So these are common names. They don't follow the systematic rules, but they're in frequent enough usage that you should be aware of them. All right, I want to say just a few words about naming salts. Because one of the really important things about carboxylic acids is their acidic character, so you can pluck a proton off of them and generate a salt. And these have names, and naming the salts isn't real difficult, so we're going to talk about it. So naming salts of carboxylic acids. So first of all, what's a salt? it goes like this for carboxylic acids. If they are put in with the base that's sufficiently strong, and there's a lot of bases that will do this, but I'm going to put sodium hydroxide in, for example, as the base that I'll use for this reaction. The carboxylic acid proton is pretty acidic, and it has a big partial positive charge, and the oxygen of hydroxide has got a big substantial negative charge. So what likes to happen is the negative and the positive like to get together, and so a pair of electrons on the OH minus comes and plucks the proton off of the carboxylic acid. The electrons go to that oxygen, and you have an acid-base reaction where you get this structure and water. So this is what's called a carboxylate salt. And we're going to learn about specific names for those. So it goes from carboxylic acid to carboxylate salt. And you can take a carboxylate salt and make it go back to the carboxylic acid by adding a strong acid, like hydrochloric acid, for example. So a lot of the chemistry of carboxylic acids revolves around taking the proton off, getting this, and then taking this and putting the proton back on. So proton on, proton off. But it's important to understand that they're very closely related functional groups. So these have names, and we're going to talk just really briefly about how to name them. So I'm going to slide this over and talk about carboxylate salt naming. Okay. So here's a carboxylic acid salt. It's a sodium salt of propanoic acid. If this were the acid, this came from propanoic acid. To name it as the salt, to name carboxylic acid salts, list the cation first. So in this example, the sodium is the cation, so that comes first. So the name of this salt would start off with sodium, and then there'd be a space, and then the name of this comes next. Take the name of the carboxylic acid that produced the salt, that would be propanoic acid. Remove oic acid and add O8. So it was propanoic acid, and it would be propanoate. Because basically what you're doing is you're taking this and you're going to get rid of it and you're going to replace it with O8. Sodium propanoate. And that's the systematic name. There's also a common name for this salt, but we won't go into those. One more quick example of this. With a molecule that is going to be familiar, most likely. Here's a reaction. I'll just show you the reaction so we can have the carboxylic acid starting material and the salt product. So sodium hydroxide is a base. It'll pluck that proton off and make this molecule, which is a salt. This is benzoic acid. So to name this, we put the name of the salt out front, or the cation out front. So this is sodium. And then we take benzoic acid and we get rid of the oic acid part and we add O8. So this becomes sodium benzoate. Does that sound familiar at all? Where have you seen it? Yeah, it's a food preservative. It's a super common food preservative. If you're eating processed food, look at the label and look for this thing. My guess is almost everybody's probably got this in a food that's in your cupboard at home right now. Maybe even in your backpack. Sodium benzoate. It's a real common preservative, and this is where it comes from. So anyway, that is enough for naming carboxylic acids and their salts. Now we're going to move on and talk about something new. Unless people have questions. Any questions about the naming? All right, let's chat about something else. Let's talk about physical properties for a little while. So carboxylic acids have this functional group on them that is rich in partial charge density, and it leads to some interesting physical properties. Essentially, carboxylic acids are very high boiling because they form a species called a dimer. Let me draw that out for you. So here's a carboxylic acid. If you think about where all the partial charges are, there's a partial minus on the oxygen there, a partial minus on that oxygen, partial positive on that carbon, partial positive on that hydrogen. So we've got partial negative, partial positive, partial negative, partial positive. It's loaded up with a lot of partial charges. And if you put two carboxylic acids next to each other, they'll try to align themselves so that these complementary charges associate. In other words, the partial positive of one is going to want to line up with the partial negative of another. That's just electrostatics. The molecules wanting to be close to each other. And the diagram that I'm going to show of this is looking like this. So you've got a partial positive here, partial negative there, partial positive here, partial negative here. And the molecule can simultaneously form two strong hydrogen bonds, which I'm going to show here is a dotted orange line. So two hydrogen bonds which are the strongest intermolecular force that we have, and there's two of them, and the molecule therefore sticks together really, really strongly. It's got very strong intermolecular forces. Very strong intermolecular forces. This is called a carboxylic acid dimer. What dimer means, and you're going to see dimer listed in biology when you start talking about proteins and all kinds of things. What it means is this is two identical molecules that are associated. And associated is kind of a generic term for saying they're stuck together somehow. These two form a dimer because it's two molecules that are held together by hydrogen bonding. So it leads to the molecule having a really high effective molecular weight, and it boils really high is the outcome. And so we're going to look at some experimental evidence of that. So I'm going to list a bunch of molecules that have similar mass, and we're going to look at their boiling points. So I have several molecules here for you. I've got a butane molecule. I've got a molecule that's got an aldehyde. Got a molecule that's got an alcohol functional group, and then I have a molecule that's got carboxylic acid functional group. So I'm going to list their molecular weight just so that it's clear we're talking about molecules that are very similar in mass. 58 grams per mole, 58 grams per mole. This one happens to be 60 grams per mole. This one's also 60 grams per mole. So, not dramatically different. And they don't have dramatically different surface areas either. These are a bit more linear. This one's a little bit more compact, but it's a fairly minor difference. Let's look at boiling points. Butane has a boiling point of 0 degrees C, which is why it's good to use for lighters. It's basically, it's pretty much wants to be a gas at room temperature. If you change one of the atoms to an oxygen like this, this oxygen enables dipole-dipole interactions. And we're going to list those later, but the boiling point for this one is 48 degrees Celsius, so it's higher. Over here, we get 97 degrees Celsius for the alcohol, and over here, 118 degrees Celsius for the carboxylic acid. And here's the difference. Intermolecular forces. Van der Waals attractive forces. That's the molecular force that everything has. They all have van der Waals. So I'm going to list that as VDW for van der Waals attractive forces. This is temporary dipoles that form that lead to weak interactions in small spaces in the molecule, but when you add up surface area, they can become big, but these are all small molecules. But they all have this van der Waals attractive force. This one has nothing else. It has no dipole-dipole, no hydrogen bonding. This has dipole-dipole. I'm going to abbreviate this as DD, just to speed up the drawing here a little bit. So they all have dipole-dipole, or all the three on the right have dipole-dipole interactions. Then this one cannot hydrogen bond as a pure substance because it doesn't have a donor, it doesn't have an OH or an NH, but this one does. So this one has hydrogen bonding, H bonding. This one has H bonding too, but it can do it in two places. So this is, I'm going to say H bonding times 2. So this is why you see this progressive increase in boiling point, because the intermolecular forces are getting progressively stronger. On the left, you've got the thing that just has van der Waals attractive forces. You go to the right, and you add dipole-dipole, and that increases the boiling point a bit. Then you add hydrogen bonding, that increases the boiling point more. You double the hydrogen bonding, you increase the boiling point even more. So it's all based on how strongly they interact because of their intermolecular forces. All right, one more physical property thing, and that's about solubility. I'll tell you a little bit about solubility because there could be a homework question about this, and there could be an exam question about this, but let's talk about carboxylic acids and their water solubility. Water solubility of carboxylic acids depends on the R group. I'll show you what I mean. Usually carboxylic acids, the R group, if the R group is hydrophobic, it's usually the case if it's an alkyl group. And this part is hydrophilic. Meaning water loving. So the molecule sort of has a split personality. Part of it wants to associate with water, and remember, the reason is it has all these charges, partial charges, which makes it water-like. It's behaving a lot like water in this sense, in that it's got all these partial charges, it's polar, basically. So how big the R group really is, it determines the solubility. If the R is small, they tend to be water soluble. And when R gets to be bigger, it gets harder for them to stay dissolved in water. And when R is large, then they don't dissolve in water substantially. So the usual rule is acids with, and I want to make sure I get this right, less than or equal to 5 carbons tend to be water soluble, at least somewhat. The smaller they are, the more soluble they are. So a C5 acid might be water soluble, but it's less water soluble than the C4 acid, and C4 is less water soluble than C3, and so forth. And then when you get to bigger than that, greater than or equal to 6 carbons are water insoluble. So there's kind of a tipping point, basically, and it's about between 5 and 6. So, and the point of this is that a lot of molecules are like this. A lot of molecules have polar parts and nonpolar parts, and they collectively determine physical properties, like how big is the nonpolar part, how big is the polar part. And there's you have to look at a lot of molecules that have both components and decide which one is more important, or how much nonpolar character does a molecule have versus how much polar character does it have. Yeah, there's a question.
Yeah, does the carbon count, does that include the carbon?
Yep. Yeah, it does. Yeah, you can include that carbon. Good question. All right. Let's talk about something else. Let's talk about their acid-base chemistry, because this is really the most important thing for carboxylic acids at this point. Later on in the course, we're going to look at other reactions of carboxylic acids where they do something else, but primarily what you got to think about when you're looking at carboxylic acid is this is a molecule that wants to donate a proton. So if you give it a base, it will give up its proton to that base. And so that's what we're going to talk about now, and just get familiar with that chemistry. Reactions of carboxylic acids. Behaving as acids. They have other behaviors too that, like I said, we're going to learn about more, but this is the most fundamental one that you need to really always remember, is that they like to give up a proton. So here's the general acid-base reaction. Let's see how I want to phrase this. I'll put this one up there again, this reaction with the hydroxide. And when you have a base that's strong enough, in the presence of this carboxylic acid that has a partial positive on its H, the base comes along, grabs the proton, and then electrons go here, and you get a carboxylate. There's a sodium salt here, and then H2O. So this is an acid-base reaction. And you can look at what's the major product, what's going to be the favored thing. Is it going to be product or is it going to be starting material? So let's look at the pKa's of these things. If the pKa of this acid is equal to 5, for example, and the pKa, so I'll just underline that H there, and then that H in water is a pKa of 14, this is a much weaker acid. This is a much stronger acid. And since this is a weaker acid, the thing it came from over here must be a stronger base. Must be the stronger of the two bases. So the reaction likes to go from strong acid, strong base to weak acid, weak base. This is stuff that we've been talking about for, we started this way at the start of the semester last semester in Organic 1. Chapter 2, we were talking about acid-base chemistry. And because these are really strong acids, they like to go in that direction. So this is a very product-favored reaction. So you might see questions where you have to predict what is the position of the equilibrium, predict the products, decide whether or not products are favored or reactants are favored, and it all depends on what's the strength of the corresponding acid and the corresponding base. All right. Why are carboxylic acids strong acids anyway? It's got to do with the fact that their anion, the thing that you get when you pluck off the proton, is resonance stabilized. So if you take a look at a carboxylate anion, this is one Lewis structure of it, but it's not exclusively like this. The negative charge is not stuck on that oxygen. It's shared with the other oxygen. And so there's a pair of resonance structures that are collectively going to describe this anion. And it makes a big difference in terms of stability. So this anion, this carboxylate anion, is stabilized due to resonance. Carboxylate anion is resonance stabilized. This makes it a weaker base. And because bases and acids are inversely related, the carboxylic acid is therefore strong. Therefore, carboxylic acid is stronger. It's stronger as a result of this stabilization. It's easy to make the anion because it's nice and stable. That means the acid is more likely to give up its proton. So we'll talk more about this on Friday, and we'll go through some review too. There's not a ton of more chemistry in chapter 15 that we're going to talk about. It's mostly about acid-base chemistry. So we're going to see carboxylic acids donating proton, and that's about it. So see you next time.